Okay, folks, I'm going to start talking about something called power functions. A power function is simply a function that looks like this, x to a power. And the powers we're going to be looking at are going to be whole numbers, 0, 1, 2, 3, 4, 5, 6, 7, stuff like that. So we won't be looking at fractional or negative powers on this. So when I'm talking about power functions, I mean the power is going to be a whole number here. Now, if you go ahead and take a look at this, I've got some graphs here on Desmos. I'm going to start with this one, y equals x squared. We all know what that looks like. That is our sort of our quintessential parabola here. It has what, a vertex there at the origin. It has a line of symmetry being the y-axis here. And this is what it looks like, okay? So it's this red parabola here. Now, I'm going to take that off here. Well, not take it off. Let's go ahead and look at another one here. Suppose I put a negative sign in front of the x squared. Then I guess it technically wouldn't be a power function, but it's going to be a multiple of a power function. In this case, that -1 there is going to have what effect? It's going to, yes, it's going to create a reflection across the x-axis. So what we end up with is that blue parabola. Okay? I hope that makes sense to you here. Here's another one we'll be looking at here. Let's pull that one off. Suppose I multiply that power function x squared by 3, then what's going to happen there? Well, that 3 is on the opposite side from y, so when I multiply by 3, I'm actually stretching in the y direction by a factor of 3 then, so that's what that should look like. Yep, you guys see that's actually stretched it out. It's made it grow faster in the y direction than it otherwise would have. Here, I've also got what the multiple is -3, so I'm getting a stretching factor of 3, and what? The negative sign makes it a reflection also. Okay, so comparing these two red parabolas, there we go. Okay, now let's pull these off here. I want you guys to pay attention to the parabola x squared, and what happens as x approaches -infinity. So I'm moving along this way along the parabola. Okay, so x is getting large in absolute value but negative, and what happens when the x gets large in absolute value and is positive. You notice that the function has what we call end behavior. The end behavior for this one is it goes from what? The upper left, okay? It goes from the upper left, comes down, and then goes back up. What? Up to the upper right, okay? So it looks like horns here. It's smiling. Now, I claim if any power function where the power on x is an even whole number, it's going to have a similar type of look as far as its end behavior. In other words, from the upper left to the upper right. So let's compare that. Aha. See? Okay? You're seeing the effect there. It has that same kind of effect. Zooming in a bit, you actually notice between -1 and 1 that what the x to the 4th power is function is a bit flatter than the original parabola x squared. But when we take values of x greater than 1 or less than -1, the 4th power function is actually growing faster than the parabola does. Okay? Now, what I'm going to do, let's take this off here. I'm going to go crazy here. Okay, that flatness comment here. I'm going to go x to the 40th power and see what that looks like. Notice how flat this looks here. It is never, it's kind of getting squared off looking if you look at it from a distance, doesn't it? It's making a pretty quick turn here, okay? It's growing really, really fast. This would not be a good graph. All right, I'm going to go crazy here. I'm going to raise it to the 400th power. What do you think that looks like? Oh, it's even sharper turn than it had before. It's growing so fast. Okay, so it's kind of funny. Zooming in here, you can see it's actually not squared off here. Okay. All right. So far, we've been looking at the graphs of these power functions. One of the qualities that these power functions have is that they're continuous. That means you can draw the entire graph of the power function without lifting your pen from the paper. So it's unbroken. It doesn't have any holes or jumps or anything like that. You can draw the entire thing without lifting your pen from the paper. Alrighty? That's continuity. Continuity. Okay? And this happens as I zoom out. That's what it looks like, okay? All power functions are going to have that quality. In fact, all polynomials that we'll be looking at have that quality also. Now, I've just been looking at power functions where the power on x has been even. Let's go ahead. Let's take this guy off here, and let's look with an odd power. You see that's actually y equals x to the first power, right? It's a little boring, the line y equals x, okay? The end behavior on this one, you guys notice, it comes from what? The lower left to the upper right. The lower left to the upper right, okay? That's its quote-unquote end behavior. Now let's go to the next higher odd power, which is the cube. And this has what? It has a little bit of a bend to it, doesn't it? Okay, it's kind of an S-shaped curve. It has the same end behavior from the lower left to what? The upper right. So as x approaches minus infinity, the function approaches minus infinity. As x approaches positive infinity, the function approaches positive infinity. Okay? Now let's take this one off there. It's kind of boring. Let's put this guy. What would happen if I put a negative sign in front of that x cubed? Technically not a power function as such, at least using my terminology. But if that negative sign is out front, once again, that's going to be what? The x-axis reflection of this. So, yep, those look like x-axis reflections of each other, don't they? Okay, alrighty. Oh, by the way, this sort of S shape here, if I punch it up to the fifth power, it's going to have the same general shape, okay? Sort of that S curve. Again, the same end behavior from the lower left to the upper right. If I come up here with this one, when I use the negative there, what kind of end behavior does this have? It goes from what? The upper left to the lower right. From the upper left to the lower right, okay? Alrighty, because of that negative sign in front. Same thing up here, comparing these two, okay? I don't know if I mentioned that on this earlier one. Here's our original quintessential parabola, y equals x squared in red. And if I use what? Negative x squared, then it's what? Has the opposite end behavior in that sense. It's going from lower left to what? Lower right, okay? Alrighty. Now, I'm going to go ahead and do this just for craziness here. X to the 75th power, what is that going to look like? Well, it's going to look similar to these, okay? But because of that high power on x, it's going to be really squared off. Let me point out that once again, when I'm between -1 and 1, the higher power function, in this case the blue one, x to the 5th, is actually flatter than what? The cube function with the lower power on x. Okay? Once we pass 1 and -1 though, the graph actually increases more quickly or decreases more quickly with the higher power on x, as you can see here. Okay? Have you thought about what this is going to look like? Okay, it's going to look really similar to these two. Maybe I'll leave the x cubed on and compare it. What's it going to look like? Boom. Yeah, really squared off, okay? Yeah. It's approaching 0 really fast when you're between -1 and 1, but it grows really quickly when you approach 1 here. So it almost looks like this a funny elbow shape, double elbow shape. Again, the same end behavior though. Alrighty? All right, so just for a little introduction there.